Thank you. I'm not going to use that because they never work for me. So thank you. We talked a lot this morning kind of about what you can't do. And I'm interested in what you can do. And before I start, I'd like to take a look around, and this is a very nice place. I'm enjoying myself. And you should contrast that with what I call the Laboratoire de Glaciologie at University of Michigan, which is that. It is portable, but most of what we do involves a computer, a cup of coffee, and a blank sheet of paper. That paper occasionally gets filled once the coffee cup gets filled. And I'd also like to point out that this title of the mathematical framework of Kant was not my choice. And so I was thinking about it. I came back from dinner last night, and I deleted all my slides and decided to talk about something different. And so I thought, well, maybe the physical framework again, I don't really like math all that much. You know, you see Christians over there grimacing. But so maybe the physical framework is a little bit more interesting. I thought about it a little bit more, and then, well, what I really care about is what the heck are the processes going on that are driving calving? And then I fiddled with that a little bit more, and then eventually I decided, calving. And this actually originally had a different word after that, but I realized that we were actually being recorded, so that would probably not be appropriate. And then I eventually came up with calving. Where do we go from here? Which is kind of what I'm interested in. And I realized I'm talking about something that's different than I was invited to. I don't know if we can be uninvited once we're up here speaking, but we will find out. I might not get lunch. And so I'm actually going to start with a very simple idea, which is that what is calving, and I want to define it. And people will normally define it as the sudden detachment or breaking away of a block of ice, right? And so that's a very simple definition. It could be little tiny stuff falling off of the glacier, or in this case, it's an ice shelf. This fracture is 30 kilometers long, it's propagating 4 meters per day, and will eventually calve off a tabular berg. And if you think that fractures are driven, that the precursor to detachment is fracturing is usually driven by stress. And so that's typically the way we've thought about that. So fractures are driven by stress. My Alaska colleagues no longer allow me to call it iceberg calving, and they insist that we call it frontal ablation. And the idea being that what you actually measure is you have a terminus, and then it moves back, and that's some combination of melting and calving. And often all we really know is that this thing has moved back, and so they think we should call it frontal ablation. I think we'd have a harder time getting funded for a workshop on frontal ablation than calving. And I don't think you can really separate these two processes. You melt and then you break. And so those two things, in my mind, are entwined. But I think it's good to remember that there's more things going on than just fracture, and whether melting is affecting the stress or doing other things, it kind of reminds us that there are places where melting is dominating the signal, and the mechanics of the ice are probably not that important. So the other thing you have to realize is that icebergs are discrete. You get a berg, it breaks off. It's not a continuous process. So this idea that we have arrows of a continuous calving rate, say, can be appropriate over some time scales, but what we often observe when we're out there is a fracture that propagates or an iceberg that detaches, and maybe we have a whole bunch of icebergs that detach, so we try and average. And if you know something about that, it's possible to say something about the long-term rates, but essentially, if it's a discrete process, we can't figure out exactly when each calving event is going to occur, then what we're going to end up with is some kind of probability distribution that the calving terminus sits at some place. And if these icebergs are big, like they are for ice tongues and ice shelves, where they're comparable to the system size, you're going to have a lot of uncertainty in where you think the terminus position is. And if your model is unable to predict the exact position of, say, the Ross ice shelf, maybe that's not such a bad thing, because we don't actually know where it's been over the past 100 years all that well. And I really don't want to talk about the specifics. I really want to ask a very simple question, which is, how do you model iceberg calving? There's a related, but not identical question, which is, how do you represent iceberg calving in an ice sheet climate model? And those seem like the same question, but they're actually very different. And the first question is really asking, how do we understand the processes that are leading up to a calving event? And so we want to go to particular glaciers or ice shelves and understand how fractures propagate, how subglacial hydrology is affecting things, how the ocean is affecting things. And we want to understand the individual processes that all sum together to give you some event over some relatively short time scale. If you talk to people like David Pollard, if you talk to people that are developing the community ice sheet model and all these other big ice sheet models, PISM, that are working on continental scales, possibly over glacial, interglacial cycles, they want to know the net effect over much longer time scales. So all these individual calving events are, for all intents and purposes, noise to them, and they care what happens when you hit an ice sheet really hard with some change. And so those aren't necessarily the same questions, and all of the detailed process understanding that you might want to actually understand what's going on will probably not ever make it into those large-scale models. But you want a representation that can somehow capture the longer-term trends. And so the first question is really a process-level question. It's hypothesis testing. What exactly is going on? The second one is, how do you go from this process-level understanding to something that's useful to someone who wants to make a sea level rise projection over centuries or longer, where you probably are not going to be able to model every single calving event, even if we understood what happened in a single calving event, which I don't think we do yet. So my view of this as a challenge, and I have no idea how to solve this problem. I should have prefaced this by saying, I have no idea how to do any of this. But we can think of this in a similar way as a spectrum of time and spatial scales, where at the largest scale, which I'm calling the macro scale, we want some kind of bulk relationship that we can give a large scale model that will give a useful result to them and not produce anything silly. As we go to smaller scales, what I'm calling mesoscale, and that's a terrible word, I can't think of a better one, what I'm calling fracture permitting. We're not going to resolve every single fracture, but maybe we can absorb the effect of fractures in some way. And maybe damage mechanics, according to the talk this morning, we can't use it once we actually have fractures, which makes it a little less useful for this. But I'm not sure I fully agree. Fracture mechanics, damage mechanics, we've talked a lot about those this morning. Those are old techniques. They've been used for a long time, and they all have their strengths. They all seem to have the same weakness, which is none of them works particularly well for the problems that we've tried them on. We're not very good at understanding how crevasses propagate yet. I think that's a real issue. And then as we get more towards the increasingly smaller scale process scale, then maybe we're actually starting to resolve some of these fractures. You certainly cannot do this for an entire ice sheet. You probably can't even do it for an entire glacier. But the stuff that people have done in terms of particle methods, not mine, which is really crude, but stuff that other people are doing has been really impressive. You can go all the way down to the crystal scale and do phase crystal methods and things that actually resolve the real physics of what's happening in fractures. Totally impractical, even for a single glacier, much less going all the way up to an entire ice sheet. So we have a problem. And I think we need to work at both ends of this spectrum. And so we can think of the macro scale. We're looking at longer time averages over on this end, and we're looking at decreasing spatial time, maybe trying to resolve individual events or seasonal trends, things like that. A consequence of that is that as we go over to these macro scale calving laws, we're increasingly abstracted from the fundamental physics. I don't see any way around that we will not be talking about melt notches in continental scale ice sheet models, because they won't have that accurate of an ocean representation. They won't resolve things at that level. But we still want to have an answer that's reasonable. As we go down here, we're increasingly fundamental, but increasingly impractical. And so we have to bridge this gap. And you can think of this as kind of like what we talked about this morning, this ductile brittle transition. We have all of these scales. There's not a clear separation of scales. But we're going to pick some range to work at. And we're going to try and understand how these different scales interact. In particular, process scale, mesoscale modeling, this is really going to tell us how iceberg handlers. I don't understand it. Maybe other people understand it much better. But I still think we don't fully understand all the processes at work in all of the different environments. And of course, the macro scale, this is what a continental scale ice sheet modeler wants you to give them. It doesn't mean we should give it to them. It's just what they're going to ask us for. We can also think about, as we get down here, people have talked about this in terms of ice weather. I prefer to call it noise, variability. And then as we get over here, climate, we have a slower time scale. And we have a trend that's driven by something. And that something, the fact that we have forcing, is important because it limits the state space that we're going to eventually hope to converge to. And really, what I think the challenge is, and I have no idea how to do this, is we want to be able to link between these different scales. And there is not a clear separation between these scales. You sort of pick some range. But if we understand what happens maybe from the laboratory, does that tell us what happens at larger scales, at individual crevasses? It should. It has not been as helpful as maybe we'd like it to be yet. And then can we go all the way up and say if we understand something about how fractures propagate, that should tell us something about the long time scale behavior. Is there some kind of slow amplitude equation that we can come up with that has a physical basis and is not entirely reliant on some kind of heuristic law that is calibrated from the lab? We may be forced to resort to empirical laws. I don't know. Perhaps you can tell me. So in my mind, I think that we still have to identify the processes that control calving. And I think these processes are going to be different in different environments. And so when you have an ice tongue, we may have to think about totally different processes than what's going on at Columbia Glacier, a temperate tidewater glacier. My guess is that we can think of limiting regimes in which some processes are more important in some environments than others. But if we go to one glacier, if we go to Columbia Glacier, we shouldn't expect that glacier to encompass every process that's at work in every place. And every time I go to one of these workshops or meetings, people spend a week arguing about which are the benchmark glaciers. I don't care that much about that. I just think we need some diversity. We also really need to identify the relevant timescales. How fast do we melt? How fast do we flow? What is actually controlling fractures? If it's the brittle timescale controlling fractures, then that's actually a little bit helpful because I don't care about the brittle timescale. I think Krista was mentioning that as well. All I really care about is where is that terminus going to be at a timescale which is very, very much longer than that timescale. So over days, weeks, months, even years, possibly decades. And if I can ignore the brittle timescale, I'm perfectly happy to. So I don't know. I don't think we fully understand how we can compute or model how crevasses or rifts or fractures penetrate, especially in 3 dimensions. There's a very small number of studies that looked at lateral propagation of fractures. We've tried to study it empirically using data. We can't understand our data, much less model it, right? Fractures speed up, they slow down for no apparent reason. They are, I think we've talked about the Columbia Glacier being a well-behaved glacier for years. These are naughty fractures, right? They don't do what we want them to do. I'm not sure that fracture is the only thing we need to worry about either. I think if you think about an ice shelf in particular, but I think other places as well, you get a crack. That crack advects for hundreds of years sometimes, and it's sitting there in the ocean. You'd be really surprised if it doesn't fill with marine ice, right? And so one of the things that is a struggle for damage mechanics is getting this healing, but I think we have a thermodynamic effect. And Wortman pointed this out 35 years ago, that as soon as you have a cold, brittle crevasse, it's going to fill with cold water, and it's going to freeze shut unless you're pulling it apart fast enough. Paul Holland's student, Jim, has been working on these models that were so disparaged by Martin the other day, in which you try and figure out what the ocean's going to do. And they did a bunch of simulations of what happens with ocean at different temperature. Can you actually burn through the crevasse? And I always dislike showing other people's work, but if you think about it in terms of ocean temperature, and this melt multiplier essentially says how much you're burning through the crevasse relative to the melt rate outside of the crevasse. So negative means marine ice formation in the crevasse, and positive means you're melting, and if it's less than 1, you're melting less inside the crevasse than outside the crevasse. And what you see is that as you crank your ocean temperature up, you melt more and more and more. And it's just because you have more warm water that's entrained into the crevasse. And so you start burning your way through the ice if the ocean is warm enough. This guy right here, minus 2 degrees, this is typically Larsen C. These are typical ocean temperatures that we see in the big ice shelves, right? I think this is the point that you were talking about, that that their JGR paper was about this point right here. This graph is incredibly misleading because the other thing that completely affects this is how fast the water is going, because that totally drives the entrainment within the crevasse. This is for a single velocity, which is prescribed from a single measurement in a rift in some ice shelf that I can't even remember because that's the only data that people have had. If we look at Pine Island, we're all the way out here. The warmest temperatures that we've seen are 1.5 degrees outside of Pine Island, and you're starting into this regime where you expect to have a little bit of melting. Bob Binschler argued that he could actually measure that in some crevasses. I'm a little bit less convinced. But there are other processes other than fracture that are affecting the depths of crevasses or damage, however you want to think about it. And I don't know if this is important anywhere on this planet or any other planet, but I think we need to think beyond just the brittle timescale in terms of what happens as a crevasse advances downstream. Is it getting deeper? Is it getting narrower? We don't think about that as often as I think we should. And incidentally, right, so we have a few points here. You know, Columbia is way out here on this graph. We should be really, of course, doesn't have a floating ice tongue. We should be really cautious about extrapolating well beyond the limits of the limited model runs that Jim did. I did this on the plane on the way over, but one of the things I've been thinking about is we go back to good old Nye's original perfect plastic approximation. The ice yields above some yield stress and it flows really quickly. Then that can be modified a little to include some cohesive stress plus a normal stress dependent friction. And if we just assume that the Columbia Glacier or any glacier, once it started to retreat, is completely fractured, maybe Glenn's flow law is not the best approximation, and we just have a glacier that's really fragmented, then we can actually relatively easily compute what the shape of the glacier would be for a given far field ice thickness, and we can evolve it over time. And I'm showing you a steady state position because that's all that really matters. And as it pulls back, I'm showing profiles computed really using an analytic solution and matching them to profiles that were published somewhere and hand digitized by me or my student at some point years ago. This is a representation of Columbia. It's not supposed to be particularly accurate. And there's absolutely no dynamics in this model whatsoever. And I do a pretty good job matching some of these profiles. Part of that is the scale. But the point I want to make is that it's easy to make a model look right, and now it's actually advanced because I'm running the movie in the other direction. I'm ignoring the width. I'm ignoring every piece of dynamics that we probably think is important, and yet you can kind of get an answer that looks more or less right. The entire profile ends up being determined by the ice thickness, which specifies the ice flux. And that's it. And so you end up with a marine ice sheet instability on steroids because your flux goes to infinity really quickly once the ice yields. I'm not arguing this is the right model. I'm just arguing that I can produce models that look reasonable easily. So I don't know how to solve this problem. I don't even know what we know for sure and what we've assumed for years, nor am I even sure what we want to know. I'm pretty sure that I want to know what happens over long timescales, and I'm not sure if I need to go to the short timescales to get that. If you like the weather-climate analogy, then a somewhat depressing corollary to that is that we do not yet have anything resembling a climate model. What we have is weather models that are run for a long time and average to give climate. I don't know if such a calving law that gives us the large-scale behavior is even possible. I don't know what the different regimes we should study are. I'm pretty sure that a guy like this is Erebus ice tongue, which is a place that I like very much because it's incredibly simple. It sticks out, it flows. There's no basal shear stress. There's no lateral drag or anything like that. It just sticks out, and every once in a while it calves off a big iceberg. One actually calved off in the past year or so. And that's pretty different than the stuff that Pfizer's done that's worked really, really well for Greenland outlet glaciers. And I can tell you that this place gets no surface melt. And if you apply a model like that based on crevasse depth, they never intersect, and this thing eventually protrudes and bumps into Greenland, right? So we're missing physics here, right? It's a little embarrassing when your glacier gets a little too long. And it was suggested that maybe fatigue is important. How do we account for that? I have no idea. A second question that I really think we need to think about is, what observations do we actually want to explain? And I think if we all thought about it and thought about the papers that we have, we'd probably all find out we're trying to explain different observations, or we're trying to explain the only observations that we have, which is often the case. The second question is, we often make models, and we often try and diagnose what's going on from those models. I think we need to start making predictions. What does your model predict that we can measure? We're often not very good at that, probably because we don't want our models to be disproven quite immediately after we publish them. But I think we need to go forward and say, okay, my model produces terminus retreat of Columbia. That should produce something that I can measure, something that I can use to falsify this model. I think we probably also need new methods. And that we have these crevasse depth calving laws. They work really good in certain situations. They seem like they break down in others. We've got damage mechanics. We've got these iceberg revolving particle models. We have fracture mechanics. Maybe we need different tools. So engineers have developed these hybrid fracture mechanics, damage mechanics that can actually resolve free surfaces. And they transition. They use the damage mechanics to get the process zone, which is not quite trivial, and then they can add water into these fractures. My experience with complicated models, whenever we do one, it looks exactly like a really simple model after a lot of work. So I don't know. I think probably other people have much better ideas. I've tried a lot of stuff, and the things that I've tried have always not worked out particularly well. So what I really want to know is, from the modelers and from the observers, and from the people that do both, which is actually a lot of us probably, what is the problem that we're actually trying to solve? Are we trying to resolve individual calving events and fractures? Can we work at both ends of the extreme? Does anyone know how to link the short time scale brittle failure, if it is even important, to the longer time scale evolution of glaciers? And is this something that we want to try and do in the review paper that we're also supposed to be writing as a result of this workshop? So I don't want to talk any more than that because I don't know the answers, and I think maybe I'd be more interested in hearing what other people want to say. The only thing which I'm going to conclude with is we've written a proposal to Reviews of Geophysics for this review paper. We haven't heard back, but I'm pretty sure we'll probably get going within the next couple of weeks, assuming everything is positive. And I would like to invite everyone here, and potentially people who aren't here, to be authors. If you're an author, I'm going to make you work. You better be back at your office on email, because I'm going to ask you to write sections, and because I think we want to actually say something new from this paper, and I don't know what it is yet, but I think we should talk about it. And I'm going to end there so we can have a little bit of a discussion.